All right, I'm just going to do a couple examples and basically show how we're going to give an idea of how we're going to use this idea of linear algebra in differential equations. And we're going to see things where we take the derivative of some function x, and we're going to have another function y, and these two things are going to be related. So for example, suppose that the derivative of x is equal to 3x plus 2y, and the derivative of y is minus 2x plus 4y. In order to solve this, this is going to be a mess to solve and work with. But it turns out if we write these in terms of matrices, it's going to make our lives much easier. So we're going to define our state variable as a vector. Notice this has an x component and a y component that changes in time. So this is going to basically mark out a path. So at any given time, I'm going to have an x and a y coordinate, and that's going to change. And that, as you mark out in time, you move along that path. I can think of our solution as a path in the xy plane. And as it changes in time, our coordinates change in time. So to be able to write this in a matrix vector form is going to turn out to be a very powerful idea. And we're going to define the derivative of a vector to just be the derivative of each component. So this system here now is going to be the derivative of x and y. And my state is xy. The derivative of x is going to be equal to 3 times x plus 2 times y. And then the derivative of y is going to be minus 2x plus 4y. So the way we've defined matrix multiplication, this is going to be 3 times x plus 2 times y. And this is, second row is going to be minus 2 times x plus 4y. And notice this is exactly the same thing as we've written above. And the question we're going to be asking now is what functions satisfy that? That's going to be for another day. But for now, just look at a quick example. So in this example, suppose I have 2 tanks. And in these tanks, I'm going to have some amount of water, and I'm going to have a salt solution coming into these tanks. And in this situation, we have stuff flowing into tank 1, and whatever's flowing into tank 1 goes into tank 2, and then it's going to flow out. We're also going to have flow back in from 2 to 1. So this is basically the system is cycling and flowing into one another. We're going to assume everything is well mixed, so that there's no gradients in the concentrations of stuff. So here we're going to have some initial volume and some initial concentration. Same thing that's going to happen in tank 2 is there's going to be some initial volume and some initial concentration. Okay, and there's going to be some flow rates coming into the system, flowing out of the system, but also flow rates between the 2 tanks. Now this is going to be very confusing because the units are what's going to matter here. And the physical quantity or the physical law that we're going to apply here is conservation of mass. And the key word is mass. So we're conserving the number of kilograms of stuff. So the number of kilograms in is going to be equal to number of kilograms out plus the change in kilograms in the system. Now, trying to apply conservation of mass with this is very difficult because we don't know these things, but because we know flow rates, we know rates of change. Okay, so what we're going to do is we're going to say the rate in is equal to the rate out plus the rate of change in the system. Okay, now this is actually going to be confusing still, and we're going to recast this so it's not quite like this. Okay, so we've got to be really careful about the signs. So when we talk about the rate of change of the system, we're talking about kilograms per time. Let's just call it kilograms per second for now. If it's positive, the kilograms in the system is going to be increasing. And if it's negative, the number of kilograms in the system is going to be decreasing. So this, what we wrote here, is actually problematic. So let's back up a second and be a little more careful. So we have mass is conserved. So these are units of kilograms. We're going to have rate of change of mass. That's going to be kilograms per second or kilograms per hour or whatever units are appropriate, but it's kilograms per time. We also are going to work with concentration. And this is where it's going to get tricky. Concentration is number of kilograms per volume, which is kilograms per meters cubed. Okay, or we're going to be looking at it at kilograms per liter. Concentration is not conserved. It's important to realize concentration can change in unpredictable ways because of the volume can change. And that makes working with volume or working with concentration problematic. So when we talk about mass conserved, we're going to say the rate out of the system. Oops, let me be careful here. The rate in is going to be kilograms per time. The rate out is kilograms per time. And if the rate out is bigger than the rate in, then that's going to be negative, so that the total rate of change should be negative in this system. So what do we have? We have then the rate into the system minus the rate out is going to be the rate of change within the system. Right? So if you have more stuff coming in, if stuff coming in is coming in at a faster rate than what the way it's going out, the total rate in the system is going to be positive. Okay, so this, when we say conservation of mass, is what we mean. And it's really important that we understand what rate is. This is going to be the derivative of the mass, and the units are going to be kilograms per time. Okay. Now, part of the problem here is we're going to have concentration of stuff coming in, and we're going to have the rate of the volume coming in. So what does that mean? Concentration then is going to be kilograms per liter. we are going to have some rate of fluid moving in at some liters per time. And the question is how do we take these two things to get the amount of kilograms per time? Right, so that is going to basically be, and we're going to essentially use the unit analysis that you saw in chemistry. So if you have some number of kilograms per liters coming in, right, so this is concentration, and it's coming in at some rate of some number of liters per time. So this is some rate of fluid flow coming in. How do you get kilograms per time? So what's the number of kilograms per unit time coming into the system? Well, let's just start with the concentration. We like the concentration because it's got kilograms in the right place. So I've got kilograms per liter there. Notice that my rate in has liters per time. So if I do that, my liters are going to cancel. I'm left with kilograms per time. So if I multiply by the flow rate, I'm going to end up with the amount of kilograms per unit time coming into the system. That's a lot. Let's look at an example and see what that means. So for example, I've got a tank. I've got flow coming in at 4 liters per minute, and there's some concentration of a chemical coming in at 4 grams per liter in the inflow. Initially, the tank has a volume of 200 liters of fluid, and the concentration is 0 grams per liters. Okay. I'm going to suppose I have a second tank. Tank 2 initially has a volume of 100 liters, and its concentration is 0 grams per liter. And I have a flow out at 4 liters per minute. And I'm assuming everything is well mixed. And finally, I'm going to have flow from tank 1 to tank 2 is 6 liters per minute. And there's going to be a flow from tank 2 to tank 1, so there's pipe running back, and that's going to be 2 liters per minute. So one of the hardest parts about these kind of problems is just organizing the information, figuring out what's being said, and dealing with it. And you have to draw a picture. If you don't draw a picture here, it's going to be really easy to lose track and get goofed up. So the idea here is I've got tank 1 with some amount of water, and tank 2. So this is 1 and this is tank 2. I have some initial volume. We'll call that V1 0. And what is that? We said is, let me be careful, this is 200 liters. And we have and now notice we're given things in concentration, but concentration is not helpful in terms of applying physical principles. The physical principle here is going to be conservation of mass. So I'm going to have x of 0 is going to be, since the concentration is 0, that means there's going to be 0 grams. So x is going to be the number of grams of whatever chemical I have in tank 1. Okay, so the key thing here is this is the amount of stuff in grams, so it's mass and not concentration. what's going on with tank 2. Tank 2, so V2 0 is 100 liters. And I'm going to say that Y is going to be the number of grams in tank 2. So the initial concentration is 0, so that means there's 0 grams in there. So let me be careful here. What information have I used? So I've used this to get the initial amount of mass in tank 1. I've used this to get the amount of fluid in tank 1 initially. So I can be careful. This is at t equals 0. This is also at t equals 0. So I've used that piece of information, and I've used that piece of information to say there's 0 grams in the tank. All right. What else? What other information do I need? I've got some amount flowing in. So it's flowing in at 4 liters per minute, and the concentration is 4 grams per liters. So I've now used that information. It's flowing out of the system. So it's here at 4 liters per minute. And that's all I know about that. So I've now used this piece of information. So the only information I have not used is this. And what the heck is going on here? So I've got flow from tank 1 to tank 2 coming in at 6 liters per minute. So I've used this. And then it's going back. Let me be careful. The direction matters. And this is going at 2 liters per minute. Okay, and so now this is my setup. So let's be careful here. So what do we have? Let me redraw this because this is a mess. I've got 4 liters per minute coming in. See that? At 4 grams per liter. I've got the initial volume is 200, and the initial amount of stuff is 0 grams. I've got a second tank. Initially, it's, let me be careful, 100 liters for the second tank. And initially, it has 0 grams of stuff in it. And it's flowing out at 4 liters per minute. This is coming in at 6 liters per minute. And then it's going back at 2 liters per minute. So my state variables are x of t is the number of grams in tank 1. Y of t is the number of grams in tank 2. But I've also got the state of the amount or the volume of stuff in tank 1. And that volume is in liters for tank 1. And V2 is the volume in liters for tank 2. All right. Let's work with the volumes first. The rate of change of the volumes is liters per minute. So the rate of change of V1 is going to be the rate coming in. So we have 4 liters per minute coming in from this term. So that's plus. And leaving, we have minus 6 liters per minute from here, but we also have 2 liters per minute coming in here. So that's 0. So that means V1 prime is 0, which means V1 is a constant. And since V1 is a constant and it's initially 200 liters, that's going to be 200 liters constant. Same thing with volume 2. It's going to be the rate coming in. So what's coming in is 6 liters per minute. What's going out is we have 2 coming out from here, and then 4 coming out here. So 6 minus 2 minus 4 is 0. So that means that V2 prime is 0, so V2 is a constant. And since it's initially at 100 liters, it's going to be a constant 100 liters. So we now have the volume as functions of time. Unfortunately, they're constants. All right. Now, what are we going to do for the... Yeah, let's do this. So this is already a mess, but well, here's what I'm going to do. I'm going to now do the amount, and again, the units here are kilograms per, well, we have minutes. So always check these. Sometimes these time units will be seconds, sometimes they'll be minutes, sometimes they'll be hours. So you got to double check that. So the rate of change of the amount of stuff in tank 1, so this is tank 1, this is tank 2, is kilograms per minute. And this is going to be the kilograms per minute in minus the kilograms per minute out. And the same thing for tank 2, is this is going to be the kilograms per minute in minus the kilograms per minute out. So how are we going to do that? So I want to redraw this again, so let's do this. So this is going to be rate in minus rate out. The only stuff coming in is from here and from here. So let's do this first. So I've got 4 grams per liters coming in. And it's coming in at a rate of 4 liters per minute. And again, this is exactly the kind of stuff you did in your chemistry class with a dimensional analysis. The liters canceled, I'm left with grams per minute. For this term here, I've got 2 liters per minute coming in. Now I need grams per liters. I want to multiply grams per liters to get grams per minute. Well, the amount of stuff in this tank is y of 2 kilograms, but it's per, and this is V2 liters. So you can think of this y of t over V2 as the concentration in tank 2. So this gives me my liters cancel, and I've got kilograms per minute. And now finally I've got stuff leaving at 6 liters per minute, so that's minus stuff leaving at a rate of 6 liters per minute, and then the concentration in tank 1 is going to be x of t kilograms per v of 1 of t liters. So again, liters cancel, I'm left with kilograms per minute. So let's clean this up. So this gives me 16 grams per minute. This is going to be plus 2y, and we said V2 is a constant 100 liters. And then this is going to be minus 6x, and we said V1 is a constant 200 liters. And this is all going to be in grams per minute. For dy dt, same thing, is rate in minus rate out. The rate in, so the only thing coming in is this 6 liters per minute. And the concentration of that is going to be what's in tank 1. So that's x of t grams per V1 of t liters. Oops, that's wrong. That's how it's, oh, that's right. That's what's coming into tank 2. What's leaving, well, I've got 2 liters per minute leaving, going back to tank 1. And that's going to be times the concentration in tank 2, which we already said was y of t divided by v of t. So this is liters, y of t kilograms per liter. And then I've got this leaving here is minus, so that's leaving at a rate of 4 liters per minute. And the concentration again is y of t kilograms per V2 liters. So let's clean that up. That's going to be 6x. V1 is a constant 200. This is going to be 2y. And then V2 is a constant 100. And this is going to be minus 4y. And the V2 is 100. So I can clean this up further. So that's 6 over 200x. This is minus 2 minus 4 is going to be minus 6 over 100 y. So let me rewrite that. I have dx dt is going to be, I'm rewriting this now, so I have my x's, then the y's, so this is minus 6x over 200 plus 2y over 100 plus the 16. These are, everything is the same units now, grams per minute. For my dy dt, I'm going to just leave it alone because it's written as x minus y. Now trying to solve this is going to be difficult. And again, we're going to find out that writing this as a linear system is going to be nice. So our state variable is x of t, y of t. On the left, we have the derivative of x and y. And I'm going to write this as a linear system. Now I'm going to have to be careful because I have plus a 16 all by itself. So because of that, I know I'm going to have a 16, and then there's a 0 there. This right here is going to be the vector given by these two terms. So my state is x and y. For the first equation, I've got minus 6 over 200 times x plus 2 over 100 times y. And for the second equation, I've got 6 over 200 times x minus 6 over 100 times y. And this is the differential equation that is expressing the number of kilograms in tank 1 and tank 2 and describing the relationship between the rates that they change. And the question we're going to ask next, or later on, actually we're going to talk about linear systems in general next, but we're eventually going to ask, how can we figure out what x and y is? In order to do that, though, we're going to need a little more linear algebra and a little more discussion about what these equations mean and how do I manipulate things of this form.